Hello friends, this video on P block elements part 2 is brought to you by examfear.com. No more fear from exam. Let's do a recap on the periodic table trends. We have done this in the previous chapter. I wanted to do a recap. The electron gain enthalpy increases as we go from left to right. Why? Because if you see, the atomic size decreases. And if you come here, the atomic size increases. This is across a period, this is across a group. So I'll just, the moment you go from here to here, the atomic size increase. So the electron gain enthalpy increase. Correct? Because these, for example, this is, let's suppose A, B, C, D and E. And this is, let's suppose C, and this is, let's suppose C1, C2 and C3. So if you go from A to E, E can easily pull electron, right? Because of small size and more charge. So electron gain enthalpy will increase as you go from here to here as compared to here. Similarly, if you go down the group, the atomic size increase, so it's difficult for this C3 to pull electron, but easy for C to pull electron. So the electron gain enthalpy is more here, less here. So if you go up, the impetus increases. Similarly, ionization enthalpy. What is ionization enthalpy? The energy required to pluck electron. So electron gain enthalpy was to give one electron. Ionization enthalpy is pluck electron, right? So to pluck electron, if you see, if you go from here to here, the size decrease. So it's difficult to pluck electron. Correct? The moment the size decrease, so the outermost electron, the valence electron, is more in control with this nucleus. It will be difficult to pluck electrons. So it needs more energy to pluck one electron. So the ionization enthalpy increase. Similarly, if you go up, the size decrease. Again, since the size decrease, it is difficult to pluck electron, right? So the ionization enthalpy. Similarly, we have the atomic radius. If you see, the moment you put down increase, the moment you go from here to here, it increase. Similarly, electronegativity also, since it is smaller in size, it can pull the nearby electrons more easily. So electronegativity is increasing. When you go up, the size decrease. Smaller is the size, more is the tendency to pull the nearby electron. Electronegativity is nothing but the tendency to pull nearby electrons, right? So that is increasing. And same thing about the metallic and non-metallic characters. So we have discussed these things in the past chapters. So if you have more doubt on this, you can watch the previous videos. Just we will be using this trend, so I thought it's a good idea to have a recap. But for more understanding on this, I seriously recommend you to watch the atom chapter where we have discussed the trends in the periodic table. Let's talk about the P block trends. The P block trends, the first is, we'll talk about the electronic configuration, we'll talk about the trends in atomic and ionic radii, we'll talk about the ionization enthalpy trends, we'll talk about the electron gain enthalpy trend, we'll talk about the electronegativity trend, we'll talk about the metallic characters, oxidizing and reducing agents, oxidation states, diagonal relationships. So this is all we'll cover in the periodic table trends. Let's start with the first one, electronic configuration. As I told, the electronic configuration for P block is NS2 and P126, right? There is a general electronic configuration for P block element. Let's see for the group 13, the general electronic configuration is NS2 and P1. Similarly, for group 14, it is, right somewhere here, NS2 and P2. For 15, it is NS2 and P3. For 16, it is NS2 and P4. For 17, it is NS2 and P5. And for 18, it is NS2 and P6. So you see, P is varying from 1 to 6. Other things are all same. Correct? That is my electronic configuration. Correct? So if you see, for example, boron, it will be what? 1s2, 2s2, 2p. Correct? Atomic number 5, 1s2, 2s2, tp1. So if you see, this is nothing but N, or I can write as boron as helium 2s2, tp1. So if you see, the pattern is similar. So if you put N is equal to 2, this is my pattern. Similarly for carbon, if you write carbon, it will be helium 2s2, tp2. Correct? Actually for carbon it is 6, so it is 1s2, 2s2, tp2. For simplification, 1s2 is nothing but helium, so I'll write this as this. So if you see, this is similar to ns2 np2, where n is equal to 2. Similarly, let me write for nitrogen now in blue. So nitrogen, it will be what? 7. 7 is what? 1s2, 2s2, 2p3, right? 2 plus 2, 4 plus 3, 7. This is nothing but, if you see, helium 2s2, 2p3. So the general trend we write is, we wrote was ns2 np3. So if you see ns2 np3, so if you put n is equal to 2, if you see, the trend is matching. Similarly, you will see for oxygen, you will see for oxygen it will be what? For oxygen the atomic number is 8, so it will be 1s2, 2s2, 2p4. So here also, if you see, ns2 np4 is the general trend. Similarly, you can write for fluorine and neon. So if you see, the trend is, the general electronic configuration is ns2 np1 to 6, but the trend is, it is ns2 np1, it is ns2 np2, np3, np4, np5 and np. Let's talk about atomic radius now. But before let's discussing the trends in atomic radius, let me talk about atomic radius. In fact, atomic radius is a very vague term. It's a very vague term. See, if you have a cricket ball, let's suppose it's a cricket ball I have, right? It's a cricket ball or football. How difficult is it to measure the radius? It's pretty simple, right? Because the boundaries are well defined. I know this is my ball, this is my center, and this is my radius, this is my boundary. Since the boundary is well defined in cricket ball, it is easy to find the radius. But in case of atoms, the boundary is not defined. In case of atoms, the boundary is not well defined. You know that? So if you don't know this, please watch my atom chapter, where we've explained this properly, why the boundary is not defined properly for atoms, because there are certain principles also which talks about that, but I just recommend you to watch the chapter. But in this, if you see, the atomic radius is a very vague term because the boundary is not well defined. How to measure the atomic radius? So typically what they do is, there are 3 types of atomic radius actually, which is quite popular with the chemistry. The first is the van der Waals radius. This is the imaginary radius actually, that is used to model an atom. For example, I have an atom, I have 2 atoms. I'm assuming that they are held by a very weak van der Waals force, right? So then I'll measure this 2 distance, because locating these 2 points are simple, correct? But this is something which is not so clear domain, because if you see the actual model of atom, the electron jumps here and there, right? So there is no fixed boundary of this, right? So if we are assuming that there are 2 atoms and they're held by a van der Waals force, we'll find a distance between 2 nucleus and divide by 2. We'll get the radius. But this is not always true, because not all the atoms we can find a van der Waals radius, right? Because some atoms are so reactive, they always form bond with some element. So it is not always possible to find a van der Waals radius. But this is nothing but, you have 2 atoms and they are held by just van der Waals force, no reaction between, no covalent or ionic bonding with them. Then this is the distance you get. So if you see right here, if you see this is blue color, so this is my blue color is my van der Waals radius. So there are 2 atoms, if you see, this is my atom and this is my atom, and they are held by van der Waals force, and I find the van der Waals radius, right? So assuming this is my nucleus, not my nucleus will be something here. This is my nucleus actually. The dark blue is my nucleus. Don't think that this big is my nucleus, right? Let's suppose this is my nucleus actually. Only this blue one. I'll draw the nucleus for all actually, all 4. Right? This is my van der Waals radius, the blue one. sometimes we also find the covalent radius. So if you see in covalent, actually in most of the case the orbitals overlap, right? So instead of this much distance, atom is actually in this distance. This is actually the most practical radius. Or for ionic also we have the same thing actually. For ionic also same actually, because in most of the case the van der Waals force is not the only force, right? There is some ionic or covalent bond. With that, the nucleus are more closer to each other. So in that case, you want to find the radius here. We'll find distance between C and D here, actually, or A dash B dash, I'll say, because they are same, just different representation. You'll find different distance between A dash and B dash and divide by 2. So what you will get is the red one, that is covalent or ionic radius. So if you see, these radius is different and this radius is different. In fact, always van der Waals radius is always more than covalent radius, or these are almost equal actually, covalent or ionic radius. So if you see, there are 3 kinds of radius now: van der Waals radius, covalent radius, and ionic radius. So which radius we'll talk about? When you talk about atomic radius, which radius do you talk about? Right? It's all confusion. So for this, there's a scientist who did some experiment on a lot of these atoms, and he gave a chart on the atomic radius. So that guy was J.C. Slater. We'll talk about this. 1964. He did some experiments on almost 1200 bonds, and he gave a chart of the atomic radius. So that is my atomic radius empirical. In most of the textbooks you see that is the radius we talk about. But for scientific experiment purpose, this is more convenient actually. So this slide was just to tell you that the moment to talk about atomic radius is a little confusing actually, which one to talk about, right? So there are 3 kinds of atomic radius. In fact, if you Google a little bit, you'll find that there are 3 kinds of radius actually, and if you go to some sites, they have also talked about van der Waals radius, covalent radius, and ionic radius. And all 3 they have shown differently for all that. I mean, they show that they are all different, right? And this atomic radius is a little vague concept. The one which is used in most of the textbooks, that is nothing but the data which we have got from J.C. Slater 1964 experiment. So having understood the concept of atomic radius, let's talk about the trends. And please note, here I am taking the covalent atomic radius. Please note, I am not taking the general atomic radius here. I am talking about the covalent atomic radius trend. So if you see, as we have told, the moment you go down the group, the atomic radius increase. You go from left to right across a period, the atomic radius increase. Why? The moment you go down, the new subcells are getting added, right? S, P, D, all the orbitals get added. So if you go from left to right here, in the same orbital or in the same subcells, more electrons are getting added, and this neutron is also becoming more powerful. So it is able to attract these electrons more, so it shrinks, right? So since it shrinks, it contracts, and thus if you go from here to here, the atomic radius decreases, and if you come down, it increases, right? Then if you see from this also, you can make out this is increasing, this is increasing, this is increasing, this is increasing, increasing. If you go from here to here across a period, this is decreasing, 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 right? So this is the general trend. If you see the values also, and please note, I'm talking about the covalent radius in picometer. So if you see, the boron has 82 picometer, it decreased 677, then 75, 73, 71, 69. We talk about aluminum, 118 picometer, decreased 111, decreased 106, decreased. Similarly, if you see, the trend is decreasing, right? If you see in this fashion now, boron and aluminum, it increased. Again, aluminum, gallium, it increased, decreased. Please note here, in some of the textbooks, you will see that. In fact, I'll show you in the next slide that it says that the atomic radius of aluminum is more than gallium. That is, they are talking about the atomic radius which was given by Slater. That is nothing but he has found the average atomic radius, average of the different atomic radius this aluminum exhibits in different compounds. right? Because as I told, the atomic radius is not fixed. For example, aluminium with chlorine, the bond size will be different. So if I have aluminium, if I have chlorine here, I'll get different atomic radius. If I have aluminium and mixed with oxygen, I'll get different atomic radius. If I have a compound of aluminium and let's suppose fluorine, I have a different atomic radius. If I have aluminium and hydrogen, let's suppose, right, I'll get different atomic radius. I have aluminium and nitrogen, I'll get different atomic radius. So he found that average of all these and he gave these figures. But this is, I'm talking about the covalent radius. I'm not talking about the atomic radius there. So if you see the normal trend here, but when you talk about the atomic radius, which was given thus later, you'll see a deviation actually, and we'll talk about that. Right? So the normal trend for the covalent atomic radius is that you go from here to here, decrease, go from here to here, decrease. Right? So now as I told, right, the atomic radius is a little tricky term. So in 1964, this guy Slater, he did experiment and he found the average atomic radius or average bond length by over 1200 bond types. He took the metallic, ionic, covalent crystals, molecules. He did all the experiments and he found the atomic radius for a lot of elements. And he gave a chart, and that chart is very useful for us, right? On that basis only, it is shown that in his chart actually, it was found that the gallium, so according to his chart, if you see, it has to increase, but according to his chart, if you see, the gallium, the atomic radius is less, that is 135, and aluminum is 143. So there was a break in the trend. So let's see why this size is less. Okay. So let's first try the electronic confliction, because that gives a good picture on what the atom is. If you see the aluminium, it is atomic number is 13 here and this is 31. So aluminium is 13. So let's write the electronic configuration. It is 1s2, 2s2, 2p6, 3s2, 3p1. Yeah. Let's write for gallium. It is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p. So here if you see 3d10 is there, and wherever you see 3d10 effect, 3d10 has, please note this, 3d orbital has poor shielding effect. So this is nothing but experimentally they have found this, right? 3d10 has poor shielding effect. Now since the shielding effect is poor in this case, so what you see here, see the reason I told you was the reason for contraction of atomic size when you go from, let's suppose, here to here in the same period was because the nuclear charge increase, right? The increase in nuclear charge, the nucleus are able to attract the electrons more. Now if the 3d10 has a poor shielding effect, that means the effective nuclear charge, let me write this word, effective nuclear charge, effective nuclear charge on electrons for gallium is more, right? Because these electrons will experience more nuclear charge effect. Why? The shielding effect is less, correct? As I told, the moment you go down the group, the nuclear charge increase, but still the atomic size increase. Why? Because the number of shells are more and these shells provide a shielding effect, and thus the size also increase. But the 3d10 provides a poor shielding effect, and that's why we have some deviation in the electronegativity also. We'll discuss this. Just understand that 3d10, 3d orbitals, the 3D is a very common word, three-dimensional movie also we have, just remember this word 3D, it provides a very poor shielding effect. So because of the poor shielding effect of 3D, what happens is the new electrons here experience more nuclear charge and they want to come closer to nucleus, right? Because the new effective nuclear charge is more on this electron, and thus it shrinks. It shrinks, the size decreased, and thus we have the size of gallium less than aluminium. right? This is atomic radius I'm talking about, the empirical atomic radius. Correct? Hope you understand this. See, if you go down the group, this in case of gallium, it had some 3d10 3d orbitals, and 3d orbitals has a poor shielding effect. Since it has poor shielding effect, the effective nuclear charge on these electrons due to this nucleus, gallium nucleus, is more. So this nucleus are having tendency to come closer to the nucleus. These electrons have a tendency to come closer to the nucleus, and thus it contracts and the size decreases. Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.